Hi everyone, I'm Shir, and I'm very happy to be here to talk about a topic that is many times overlooked and that once adopted properly can be a game changer in the ability to train and deploy trustworthy machine learning models in an efficient manner. So I'll start with a bit about myself. I'm a graduate of the IDF's Talpiot program, which is an excellent program for technological leadership. So after about 3 years of training, we graduate like 50 people and then start a relatively long career in the security forces, leading quite cutting edge tech areas. Personally, I started in Unit 8200, did some low-level cyber research, and gradually I was lucky to continue on and transition to data science, which since then has become very close to my heart. I was working relatively where it was still in the early days on various projects mainly for anti-terror related use cases. And it was really a great challenge to see both the value from the machine learning models and also the different challenges in making them gradually more adopted and being able to verify that they're more trusted by their users and how do they scale, how do you verify they work properly. And that was a big motivation for founding DeepChecks along with Philip, my co-founder. And in DeepChecks in general, we work the notion of a continuous validation for machine learning models. So it means from training to deployment to also have a commercial product in monitoring and production debugging. And as you probably understood by now, this is a topic that is very close to my heart, how to verify and validate and help machine learning models work better. And we're exactly going to talk about that. So just a bit more about me. When not training models, I love training in general. More standard sports is running, which I actually just came back from a run, which is nice. And also a bit less standard sports like kite surf and skiing. And if you wander around the streets in Tel Aviv, you may see me on my unicycle, either the electrical one or my non-electrical one. So I wanted to start with a short example. This is a paper from 2017. It was published by a prestigious research group in Stanford, led by Andrew Ang. And the topic was they built a network to diagnose pneumonia. Of course, it worked great and it hit the headlines and everything. Everyone was really happy. And again, you can see November 2017. Only if we go a bit into the details of the paper, and thank you, Santiago, for this tweet. Just for actually, I saw this just recently. So we have here like the area describing how they built the training set and what exactly was used. So we can see that we have 112,000 X-ray images, which is fine from 30,000 patients. So we understand that there's like more than one image for at least some of the patients, which is not a problem. But if we look at how the data set was split, we can see it was randomly split into 80% training and 20% validation. Wait, so we had the same patients that some of them appeared both in the train and also in the test data sets? This doesn't sound that right. I mean, seems like there was a potential here for basically some sort of leakage. Maybe it didn't, we don't exactly know. Maybe the model could have used some patient-specific things to actually understand what happened, especially if it's likely that the same X-ray images maybe were indications of the same thing. So in this case, by the way, it was fixed. So what you see here is a new paper that was published some time after it, in which you can really see that they randomly split the data into training with some of the patients only in training and some of the patients only in validation and test. And they emphasize that there's no patient overlap between the sets. But of course, if this can happen in such a so many researchers and such a well-known group, and it was only actually discovered a bit later, we can understand that these sorts of problems may be something we want to look and think a bit about. And if we look at this slide, we can see that there are really many additional problems that machine learning models face when they're not properly validated. So I won't go to all of these, but you can check. We have a nice blog post talking about many of the known machine learning failures. Of course, these are only the publicly known ones. There are also many additional ones that, just like internally in a company, there was some problem and then they discovered it. So this leads me to the topic of our talk. So we're going to talk about testing and how to properly test start with a short introduction about how this looks in software, because essentially machine learning is some type of software, and it's a well-known and developed methodology. Dive into testing machine learning. So what are the challenges, the specific types of problems, how to approach it, what should we test, how should we test, and when to test for? And we're going to touch about some tools for actually incorporating it into your machine learning workflow. So a bit about software tests. If you look kind of along the years, this is a field that gradually evolved. It started with a manual QA at the end of the development process. And there's lots of methodology today that really helps us do it much more as part of the development process. We put a lot of time for it. It's the responsibility of whoever develops the code. And it's really basically helping us build much more agile code with quicker iterations and trustworthiness. And this pyramid it's a well-known kind of a form of different types of tests. So unit tests for more specific things, and as we go up the pyramid, we're like testing the system in bigger granularity. So what this comes to think about is, so how and why should we do it in machine learning? So, well, about why, there's many good reasons. Starting from mitigating lots of known risks that we have, because machine learning pipelines are complex with lots of moving parts, and obviously, as we saw and as we probably are familiar with, they break. It can help us improve our process, so retrain models and deploy them much more quicker, and of course, increase our own and our users' trust in our models. And the real reason I want to talk about this, and it's so important, and also generally working in the field, is that I feel it's super important. When you do it properly, you can really improve a lot. And sadly, it's not that common. So it's not common at all, but really there's a lot to advance and improve in that area. So we're gonna dive in. If any of you were wondering, okay, so why shouldn't we just do the same things as we do in software, or aren't the challenges essentially kind of the same? So I would want to pinpoint a few of the big differences, which makes it really, in my opinion, both quite challenging and also a bit harder to sometimes use some of the existing methodologies. So in software, essentially what changes is the code, right? So maybe you added some things or you changed things, but you can at least track it and see what exactly changed. While in machine learning, you have both lots of many parts, and also the code just builds a model, and then the model is the one that's running, and it obviously changes completely. So how do you compare that, or how do you make sure you covered like all of the, for example, changes in the new model? When we look at the concept of coverage, so in software, you can at least kind of see which areas of which branches of code you covered, and it gives you some aspect of how well this code is tested or how complete. While in machine learning, it really doesn't exist. Like, what is coverage? Or am I trying to cover the input space, or rather like the different weights? Or so I can't really like make sure I covered everything, or I can't really even get an estimation of what is the percentage of what I covered. And my favorite one, or more likely like the most painful one in my opinion, is that it tends to fail silently. So the pipeline doesn't tell you like, okay, this value now changed, and continue to send over values, but they're just not right anymore. I mean, the model will give a prediction, and the prediction will go on, and no one comes and says, like, it doesn't just break. I mean, if it would just break, or in many of the cases, it doesn't just, and sometimes that would be much better, because at least we would know. And here we can really have a like gradually incurring problem and loss over time. So where does this meet us, like in our, for example, work as data scientists? So we're gonna look at a short story about Tom. Tom works at a company developing a smart and adaptive firewall, and he's really excited to work on a new project. They're going to work on bot detection. So essentially, the model needs to classify whether like certain packets of traffic are from human source or from a bot source. This is very interesting for the company because they want to be able to like divert bot traffic and not allow things like scraping of their websites and so forth. And since bots are quite frequent, so they have like the target metrics for this project are, it has to achieve a very high recall. So we really want to like over 0.99. So we really want to be able to like catch almost all of the bots, or like a very high percentage of the bots, so 0.99%. And for the precision, well, we don't like, what happens is if a bot is detected, then it's diverted to a captcha. Now, if a human is moved to a CAPTCHA, then it basically hurts conversion. So you wouldn't want to like just send all the humans over to a CAPTCHA because you would get less interaction with your website. And therefore also precision is very relevant. And here the target was 0.8. So let's look at Tom's project. He worked on, he collected lots of data from different sources, like they have some kind of, thing in the, like a toolbar that collects different data, and they have some proxy and firewall. So he got lots of like different fields of data about the traffic and the packet from different areas in the like of the product of the company. Then he went on to try building a model. So he split the train and test and did some pre-processing. And once he had like an initial model that looked good, he decided that looking at like the dynamics of the traffic and how it changes, the best idea is to retrain it every day, since the internet is very dynamic, and to use the last 8 days of traffic to train. One of the reasons for that is that there is some like typical behavior for certain days, and then if you take the last 8 days, you get like twice the same day. So that was he saw that achieved good results when like looking historically. And finally, this model was trained on lots of different websites, but when used in production, it was also used like for serving also on new websites that it wasn't trained specifically on them. So this is a happy story. And Tom finished and trained a great model, achieved the targets he needed, and the model was deployed to production. So maybe I can end my talk, or not really. Wait. What happened here? So what you see here is the model's real recall and precision after it was in production for some time. Unlike the stats we saw before, which was what Tom thought like after he did the test set and saw like what the model achieves. So there was a really big gap between what they thought was going to happen and reality. So what could have gone wrong? Let's have a look at the different phases. So for the data source, we said that there's like different types of tools developed by different teams. And what happened here was there was an API update of one of the different like tools that collects different the results, and the number was calibrated differently. So instead of being between 0 to 1, it was suddenly between 0 to 10. So again, the model continued to work, but basically it was receiving like irrelevant values. So we had here a data integrity problem. For the train test split, this may remind you of something a bit from before. So without noticing, he put this traffic from the same unique devices, or in this case, like the same unique sources, in both of the train and both the test. Therefore, this also was basically some sort of leakage and showed us essentially higher results on a test set than in reality. About the model retrain, so this sounds fine, right? Like, what is the problem here? So what Tom didn't know was that there was a marketing just launched some campaign. So it was marketing like of the website they were serving, or a various website. They launched a campaign targeted for Android users. So what happened was that there was much more traffic coming from Android than before. Of course, this change of behavior, suddenly the model just didn't behave like predicted differently, or basically predicted on different data. And many of the Android users were classified as bots instead of, though they were just like human beings coming from the source of the campaign. So this is a sort of data drift. In this case, there was a reason for it, but essentially it's just a difference between the distributions on the data it was trained and when it was in production. And serving familiar and unfamiliar websites. So what does that mean? Like, will the model essentially generalize properly for all of them? Maybe upon different segments, the performance varies a bit, and that is really what happened. Like on the websites that it already knew, it worked good. Also on some of the new websites, but not on all of them. So if we can, if we look together at all of the different problems that, in this case, they weren't necessarily all discovered exactly on the same day. I mean, when they started to understand, okay, what's wrong here? So after quite a tedious process of research, they understand different problems that happen, and really eventually were able to improve the model and the performance also in production. But this is kind of a longer motivation story about where it can meet us and how we see it in reality. So we're going to now move to talk about how to approach it. So we talked that we'll talk about the challenges, and then now about what should we check, what are the types of problems, where should we work on it in the pipeline, and so forth. So we'll start with the simplest question in my mind, which is, what should we test? So like we said, there's lots of moving parts and each of them affect. So let's have a look. What do we have here? So in a machine learning model or pipeline, essentially we have data, we have the process, the pipeline, building the data, analyzing it, building the model, and we have the model itself. And also, as we saw in Tom's example, we have also things from the environment that affect us, whether it's like things like a marketing campaign or just like the dynamics of an environment, how quickly it changes. And we may have some various constraints, for example, business constraints. Only in reality, it's a bit more complex because these things really greatly affect each other. I mean, the model is obviously built on the data and the process and so forth. And that's one of the reasons we're going to now try to like make it a bit more organized and understand, okay, so what exactly are we going to test? So in order to know what to test, I want us to have a look on what are the types of problems. So I mentioned a few examples. Let's see typically what are the different types or areas of problems. So the three groups, the three typical groups are things that have to do with the data. So specifically like the data's integrity, for example, missing values, changes in the strings, maybe incorrect labels, for example. This is something that is like a data integrity problem, which is very specific to machine learning models. Just like in general data, you don't necessarily have labels, and therefore, so there's like a wide variety of data integrity problems. Some are more general, like format inconsistency, and some are really relevant to the fact that there is a model that is going to be trained on the data according to labels. There is data distribution problems, just changes or leakages, drifts, and so forth, and things that have to do with the model's behavior. For example, does it degrade over time? How does it behave across different segments? Is it calibrated, and so forth? And I don't want to overwhelm you too much, so I'll just show this for a second. This is a very partial list of types of problems that we've seen or are familiar with, and also recommend testing for, and I'll touch a bit more. Let's look at two or a few specific examples of how it actually looks. So in this case, like we have a loan model. We're trying to classify or decide whether a loan should be approved or not, and we have various data like age, income, what is the amount of the loan, and so forth. And the model gave some prediction, and we have here another sample. Those of you that are sharp-eyed maybe already noticed the difference, which is United States. So actually, there isn't even a difference. It's only written differently. But if this is something that we didn't catch in a pipeline, then it's like, for example, let's say we have one hot encoding and we didn't first normalize the strings. So this will be considered as a probably different, like new category. And accordingly, also, you can see that the prediction is different, which is very weird. Like we would obviously expect a similar prediction. And this is a type of problem that we call a string mismatch. Another example is, well, I already popped here up the difference, which is you see here that the only thing that changed between the two samples is that instead of female, it's male. And again, the prediction is very different. Here, it's a matter both of what is the training data and what is our policy, and how do we verify these types of things. For example, if we want to make sure that the model behaves similarly on different demographics. So this is an issue we should take into consideration. And I'll give also a computer vision example. I'll say something kind of general. We do see that the same types of problems appear in different types of use cases and different types of data, whether it's a tabular, computer vision, NLP. Obviously, for some of them, the algorithms for actually catching them, or how do we analyze it and how do we verify, many times the implementation is different because we're processing a different type of data. But it's quite surprising to see that it's essentially the same areas and same types of problems. So maybe some of you are familiar with this example. It's from a famous paper called Why Should I Trust You? And here we had a relatively simple classification model that is trying to determine whether the animal is a wolf or a husky. And they got really good accuracy score. And what did happen here, though, is that once, initially, okay, good accuracy, so great, we can continue, right? But when the misclassifications were inspected, they noticed that what actually happened was that there was a big effect of the background, or in this case, like a snowy background, on what was actually predicted by the model. And essentially, so you can see, like, for example, here on the bottom one on the right, a husky was predicted to be a wolf. And it's really on a snowy background. So in this case, we have a really good model theoretically with good performance. But think about it. What if it's now deployed on North Pole, right? So probably it won't be actually that good in really distinguishing between huskies and wolves, as we believe or thought it was. So we understood that there's different types of problems, but how do we approach it? What should we test? And sadly, if you Google it, probably you won't find too many results. You have different ideas or implementations, but it's really not that well built. And we're now gonna go over the different parts. Hopefully, by the end of the lecture, you won't need to feel lucky, and you will have the tools to really start working on it. So, what should we test? So we should understand what are the inputs we want to test. What are the type of checks? What do we actually want to check for? When do we want to do it in the process? And is there some methodological way, or how do we really incorporate it? So about what should we test? So we saw this before, and if we really look at what are the things, we understand that there's essentially three things. There's the data, everything that has to do with the data, everything that has to do with us splitting the data, whether it's train test or also, for example, in production, it's okay, their training data versus the inference data. So any kind of batches or data splits, and things that have to do with the model. So these are the inputs. Let's look, and we have here a list of checks. If we organize it to the more high level one, we have here the different types of titles or groups of checks. So I will give a few examples of, okay, so we understood there's a problem, we understood how it acts, but how do you find it? So I will say that in general, in deep checks, we have an open source package, which you're welcome to use. And of course, you can also implement the test in any other way you choose. I'm just going to show the different types of problems that we saw and how they would look in this case with the checks. So remember the leakage that we had of the same patients in different data sets, both in train and both in test. So in this case, what we can do, of course, we have to think about it and define it, but we can verify that there aren't the same, for example, indices, both in if each patient has a unique index, so that they don't have the same indexes both in train and both in test. And in this case, we see that running this check, we see that in some cases they do. So for the wolf versus husky, we did something similar. We took a data set. In this case, these are a few pictures from the data set. And what we saw is we tried to see if there are any other meta properties or kind of meta data about the picture that can help us identify or are highly correlated rather with the label. And in this case, what we see here is that there are a few indications. For example, how green the picture is or how bright it is, highly correlated with the label. Now, this doesn't necessarily mean that the model is wrong or that there's a direct problem, but it is something that we want to further delve into. A string mismatch, so, well, we can check and verify that all the strings are the same. Feature drift, in the targeted marketing campaign, so we can really both look at a whole data set kind of level or per feature and see, wait, if we compare these train test splits, is their distribution the same? And for example, in this case, we can have a sort of aggregated drift score and verify that it behaves as we expect it to, or maybe it's a too high of a drift. Weak segments performance is something before when we saw, wait, does my model behave the same on different areas? So in this case, obviously we all check the overall metric and performance, but we can verify how does it look across different segments, whether it's segments we define manually on specific demographics, or also automatically find segments that are weaker and compare their performance. And so this is again the higher level list, and my real tip is to think about this regarding your domain, your specific task, and to build a checklist. I can also recommend think about what do you want, and also if you saw some type of problem that in the past, then you would obviously want to add it to your checklist. And what I recommend in this case is also feel free to check out our docs. We have quite a long list of checks and problems that can give you some inspiration. About when should we test? So my short answer to this is as soon as possible. Essentially, if we look at a machine learning pipeline, we have the research phases, we have the decision to deploy it, and maybe some type of CI/CD process, and the monitoring part. And what is quite typical, like, and that was something that was very surprising for me, is that we saw like companies that are monitoring their models, but not necessarily elaborately testing them before they're deployed. So the idea here is as early as possible, and some of it can already be done in the research. For example, once we have like already data, we can check the data, and once we have some initial pre-processing, we can compare like the different splits, and once we have the model, we can evaluate it, and so forth. So the last thing I didn't touch deeply yet is what's missing, how to actually do it, how to incorporate it. One of the reasons I didn't touch it is that here there isn't a very clear direct answer. It's really more dependent on your use case, what are your challenges and how it looks. I will give though a few considerations. So for example, the tests can be automatic and like run as part of the CI/CD, or they can be manually inspected. Should they have a clear pass-fail status? Maybe some of them should, and maybe some of them need, again, some like manual inspection to verify, is this what I expect? Are they run like once, or is it something that we want to constantly check, for example, when the model's in production, so every day? How are we going to verify the results? Is it like a peer review process? Is a manager, like a data science team leader, checking along with the team? Or is it, again, some like in an automatic process? And something that really helps is how reusable are they? So if we have a good base of code and a good methodology and framework, then we can it can be much more efficient to test widely. And since it may be a bit overwhelming, my really like a big tip would be to start with setting up a testing process for at least one of the phases where it's more critical. And after you feel comfortable with it, like one phase in the process, whether it's, for example, in CI/CD, or on a specific, like every time you get new data, and then continue on and really elaborate it, because I do feel it's one of the most essential parts in really building good models that work over time. So a short, some tools that you can later kind of Google or think about and how to incorporate it if relevant. In general, I split them to two types. One is for running and automating tests, and the other is for actually building the test. So in automating, we have, probably some of you know, like Python testing frameworks, for example, a PyTest or a hypothesis, workflow management tools, more for the engineering side of like Airflow for timing different processes, or also CI/CD to really run it, for example, for every new model version, such as GitHub Actions and Circle CI. And for building the test, there are a few tools for data integrity. I think there's also at least one talk about the Great Expectations in this conference, and PyData. And for ML testing, I'm happy to say that though like a year ago, there wasn't anything out there. So today, with lots of help and contributions from the community and lots of feedback, I'd love to, if you do use, to hear your thoughts, and also welcome code contributions, and I also give some examples from deep checks. So, short summary: testing machine learning is important. There's lots of recurring types of problems. We recommend to start like thinking about the inputs, what exactly you check, when you do it, and insert it into your process. Checking the data, the splits, and your model, and really throughout the life cycle, at least eventually. So on that note, I'd want to thank you for listening. Hopefully, I'd love to see you in our community, or in general, I'd love to hear your thoughts about testing and about different problems that you faced and how you've solved them. And it's also a good opportunity to say a big thank you to the community. And feel free to reach out. You can scan the QR code for more details about how to reach out to me. And that's it for now. I think I have maybe like 1 minute. So if there's any open questions, I'd be happy to answer.
Thank you, Shir. I think this is a very important topic that we need to, I've always thought that we need to do more of. So let's very quickly go for one more question. So this is from Bruno. You mentioned a couple of differences between software and ML testing. Another one of them is randomness. Do you have any suggestions on how to deal with it?
So I'd split it into two. One is, I think, in some places where it's relevant, try to really make sure that it's your pipeline is repeatable. So, for example, if you want to verify compared to some golden set or something like that, then make sure to put a random seed in place and things like that on one hand. And on the other hand, I think that really dealing with randomness is being able to do like different types of of like don't only check it once, but for example, check different splits, and then check also the variance between them and things like that. So like take into account the randomness, know that it's random, and then think how to verify your system albeit the randomness.